Hi, today we will learn optoelectronic devices. There are two such devices, photodiode and photovoltaic cell. This is also called solar cell. So firstly, what is this optoelectronic devices? Opto means optical means light, electronic means controlled flow of electron. These two branches. When these two things are jointly discussed and applied, then such a branch of physics is called optoelectronics. So, today we are to discuss photodiode and photovoltaic cell. Here you can see the symbol of a commercially available a photodiode. Here you have a photodiode with one electrode very large and another small. The large one is considered as positive. It is connected with positive of the battery, and the small electrode is considered negative. Now this photodiode is covered with, encapsulated in a transparent cover, plastic cover, so that light may be made to fall on it. From here, light can fall on this portion, and then it can affect the current in the circuit. So this is your photodiode. The symbol of photodiode here you can see. A simple diode, a triangle with one vertical line. This is a simple diode, and when you mark two arrows falling towards the simple diode, then this is your photodiode. So you can see how on illuminating a photodiode the circuit is completed and the bulb starts glowing. Yes, here the circuit has been completed. Again, it is illuminated with the help of matchstick, lighted matchstick, and the bulb again starts glowing. It means that circuit is completed. So now let us consider what the photodiode is. For that, let us consider the simple PN junction, because the photodiode is made out of a PN junction diode. Here you have a single piece, and on this single piece there is developed N type of semiconductor and P type of semiconductors on the two sides. Here let me show you what is N type of semiconductor. So when you, let me resize it. Okay, here you have one P type of, okay, this is your N type of semiconductor. You can see at the center there is written there is written 5. So here is an impurity atom sitting all around pure silicon atom. Silicon has its valency 4. You know, silicon has atomic number 14, then 1s2, 2s2, 2p6, 3s2, 3p2. So this is the last cell in which you can see you have 4 valence electrons. So each silicon atom is sitting with its 4 valence electrons, and you have one impurity atom inside it of pentavalency kind. That is your one example is your phosphorus. Phosphorus has 5 electrons in outermost cell. So here you can see that 4 electrons of phosphorus out of 5 are making covalent bond with the near its silicon atom. here covalent bonds are made. And you know, for stability, you need to make a octet. These atoms need to make octets. So octet is made. Here you can see that 8 electrons are there and they are shared in between. So there is octet made, and the fifth one electron out of these 5 electrons, 4 is making your covalent bond and 1/5 electron is left free. And since these are bound electrons, these atoms and this nuclei is totally bound, this electron becomes rather free. It is free to move in larger orbit. It is free from its nucleus. So this is one electron sitting here. These are the free electrons. So from one impurity atom you have one such electron, and there are many impurity atoms. You have few part per million, few part of these impurity atoms per million atom of these silicon or germanium semiconductor. So you have increased number of free electrons, and when you place a impurity atom, when you dope with trivalent any impurity atom like aluminium, which is having valence electrons 3, then you will find that it is making covalent bond all the sides, but a vacancy is left behind over here, that is hole, and this is taken as positive charge. So all the positive charges are along another side. So now here see what happens. Here two phenomena happens. Here you have large concentration of n-type electrons in n-type semiconductor, and here on the other side you have large number of holes. So there is a concentration gradient. When you mix any sugar syrup with water, it immediately mixes with each other. Simultaneous mixing. This happens here. There is concentration gradient, and due to which a current starts flowing, that is called diffusion current. Due to concentration gradient, diffusion current. And this is one kind of current, and that flows from higher concentration side to lower concentration side. Here it is in majority. Here the positive charges are in majority, you can see. But when some positive ions, holes, diffuses to other side, it becomes minority here because these are less in number. Here coming here it becomes minority. Okay, so this is one kind of current. This is your called diffusion current. Now one more phenomenon happens here, and that is called drift current. So let me delete first of all this thing. So second current is also created, and due to this electric field, look how. You know that when you have positive charges along one side and negative charges along another side, just like here in a battery, positive electrode and negative electrode, you know that a potential difference is generated in between the two electrodes because of their positive nature and negative nature. So here you have a potential difference created in between the two sides, and only due to that you know that electric field is away from positive charge. So an electric field also is created. Now this electric field drives the electron opposite to it and holes in the direction of it. So holes are made to move in the direction of electric field. Holes goes along this side and electron tries to come along this side. And which hole? You can see that these holes are less in number. So when less number holes are going there, any movement of charge, so obviously it will constitute some current, and that current is called drift current. So initially you had diffusion current, now you are having drift current, and this is in a direction just opposite to direction of this diffusion current. Diffusion was along this side and drift is along this side. So two currents are taking place, and this drift is due to electric field. Due to electric field, the drift current. Okay, so you have here two currents. Let me delete it because I have to write something. So you have two currents. Now when the junction will be made? When the two currents will become equal, then current net will become zero because the two current will cancel each other. So net current will become zero. And then only this junction is made. Initially the junction was not made. When current becomes zero, then PN junction is made. So here net current is zero, but current is not zero. Current is still flowing. Drift current in this direction, diffusion current in this direction. It goes on flowing, but the net current remains zero. So this is your PN junction. Now what happens when you apply a reverse bias? What is reverse bias? When positive side is connected with negative side. Positive is connected with negative side, and negative is connected with positive side. This is your drift current. This is your reverse biasing. Okay, this is your reverse biasing. So in reverse bias, what happens? Initially you had two currents, diffusion current and drift current. And when you apply reverse bias, then what happens? Here you have negative side and here you have positive side. The field will be increased and the potential will be further increased. Now you have del V2 and which will be greater than del V1. Potential has increased. And this potential is not prohibiting the drift current because the charges are falling down in this potential hill. It is not going up. The charges which is going up are diffusion charges. These majority charges are to go up. So they will be barred. When potential hill is very high, then this majority charge cannot just jump this potential barrier. But this minority charges are to fall from this potential hill. They are going down from the potential. They do not stop. They still goes on flowing. So when you apply reverse bias, so you find that reverse current appears. Actually, the reverse current was not created by this potential. We learned Ohm's law, V is equal to IR. On applying potential, current develops. But scenario here is totally different. This potential is not generating these drift currents. This drift current is already there. This potential is just barring the diffusion current. So diffusion current is not cancelling the drift effect. So drift effect appears clearly. So let me show you. Here we have a diagram of reverse voltage. And here you have drift current, or you can say reverse current. And this is of the order of microampere. So you will find that this remains almost constant. When you apply certain voltage, current is same. You increase the voltage, you find the current remains same, nearly 0.1 microampere. So you go on increasing voltage, but current almost remains same, because this drift current does not depend on applied voltage. Applied voltage only just prohibit this your diffusion current. Majority charge cannot now cross this potential hill because reverse bias has increased the potential hill. And drift charges has to fall the potential hill. So whatever be the height of potential hill, the charges, drift charges will have not any problem. So now the next phenomenon, what will you do? Now here you will apply certain electric field. Here you will apply EM radiation on this PN junction. EM radiation is falling on it. Now if the EM radiation has energy greater than 1.1 electron volt, because why 1.1 electron volt only? Because the covalent bond strength is 1.1 electron volt for silicon. Silicon has bond strength 1.1 electron volt, and if it gets 1.1 electron volt, these valence electrons, bond electrons, which are bound with covalent bond, they will be broken. So here you have not mobile charges. Mobile charges are already shifted. Here in your depletion region, all the charges are bound charges, and with bond strength 1.1 electron volt for silicon. So if radiant energy is having photon with energy greater than 1.1 electron volt, so these electrons and holes, after gaining energy more than 1.1 electron volt, then they will be broken, the bond will be broken, and here there will be formed electron and hole pair, new electron hole. Because when a bond will be broken between electron and hole, you will have new pairs of electron and hole. So electron and hole pair is formed in the depletion region. This is the one phenomenon. And what is the next phenomenon? These electron hole pairs are forming in electric field. So under the influence of this electric field, the electrons will be moving opposite to electric field in this direction. The electrons will be shifted here, and all the positive ions are moving in the influence of electric field, in the direction of electric field, and all the protons will come along. Protons, no, these are positive ions, will come along this direction. So there is movement of charges. And if there is movement of charges due to this light radiation, so this light radiation has created a new current, and that current is called short circuit current. So initially you had a reverse bias current, that is also called dark current. This is your D stands for dark. That was your dark current. And now due to illumination of EM radiation, some electron hole are created and they are moving. So a new current is constituted, and that current is called short circuit current. And you will find that this dark current does not depend on reverse bias voltage. You go on increasing voltage, but current remains same. So dark current does not depend on voltage, and even this your short circuit current, this also does not depend on reverse bias voltage. That Ohm's law suggests that V is equal to IR. When you increase V, I should be increased, but this does not happen. So short circuit current depends on intensity of this EM radiation. When you increase intensity of EM radiation, then current also is increased proportionally. They are directly proportional. So then energy, how much energy should be given to overcome a bond strength of the value 1.1 electron volt? So let me find the energy of incident radiations. And one more thing is important, that intensity of light is proportional to current. So where intensity lies, when you will see sunlight, there is yellowish appearance. Why? Because yellowish colored light has nearly maximum intensity. So now let us find the energy of a photon. Energy of a photon is equal to Sc by lambda. When you will put the value of this Planck's constant 6.63 into 10 to power minus 34, value of C 3 into 10 to power 8, and wavelength of visible light, which nearly varies from 400 nanometer to 700 nanometer, or in some books it is written that it is nearly equal to 800 nanometer. Okay, so when you will put all these values, you will find that energy varies from 1 electron volt to 3 electron volt. So this 3 electron volt or even 1 or 1.5 is more than energy gap in silicon, bond strength in silicon, that is equal to 1.1 electron. This much energy, even energy of yellow light, which is more than bond strength, that is equal to 1.1 electron volt. So getting this energy, silicon covalent bonds can be broken. And when silicon bonds are broken, electron hole pairs are formed and they are moving in the influence of electric field created in the depletion region. And when there is motion, there is current. And this current is called short circuit current. Now, we should choose semiconductors of energy gap nearly equal to 1.5 electron volt, because we have energy of visible light of ranging from 1 to 3, and the average of this is 1.5. So if we are having a semiconductor of energy gap with this value, then photodiode can be made by those semiconductors. There are such semiconductors which are very useful in photodiode: silicon, with energy gap 1.1 electron volt. Gallium arsenide, that is with energy gap 1.43 electron volt. And similarly you have cadmium telluride. It is having energy gap 1.45 electron volt. All these three are very suitable for making photodiodes. Now, this was about energy gap, but this is not wholly very important. There are another important topics, things. Optical absorption. Light is falling on semiconductor and on PN junction, and if it is not absorbed, then all these things, incidents will not take place properly. So another important thing is optical absorption. And then yet another very important criteria for selecting semiconductors for photodiode is electrical conductivity. So all these things are considered, and therefore gallium arsenide is also a very good photodiode. Availability and cost also matters. Now, next question is why reverse bias? We know that in forward bias we have current of the order of milliampere. In reverse bias we have current of the order of microampere. Now this your EM radiations create short circuit current of the order of microampere. The current generated I short circuit due to this radiation is of the order of microampere. So when you measure the current while putting the photodiode in forward bias, then also photocurrent will be created, no doubt. Photocurrent will be there, but the photocurrent will be of the order of microampere. So when you will have a milliampere ammeter, then this microampere current is not even noticeable. You cannot notice this small current with milliampere. When you will have a bulb or anything in the circuit, then you will find that photocurrent is unnoticeable. But when you apply the photocurrent and in a reverse bias, so initially the current was 0.1 microampere, and when you illuminate the diode with EM radiation, this current will be increased. It will become 0.2 microampere. So you will find that photocurrent is proportional to intensity of light, and photodiodes are here to find the intensity of light, to just count the intensity of light. So for finding intensity of light, if current becomes 2 times, we can find that okay, the intensity of light becomes 2 times. Here you have a current versus reverse bias voltage on different intensities, I1, I2, I3, I4. So when intensity of light incident on photodiode is large, then current is large. When intensity reduces, current also reduces. So you can say that intensity of light is proportional to the current flowing through the conductor, and current versus intensity of light. Since current is generated by intensity, so better you should write current here. Current versus intensity is a straight line because they are directly proportional. Now photovoltaic cell or solar cell. This photovoltaic cell is similar to photodiode Both are acting in reverse bias. But what is difference? The difference of a photovoltaic cell and a photodiode. It has large surface area and it has no biasing. No biasing. Means a battery is not connected. Now here you can see that the lower part semiconductor is actually P-type silicon semiconductor. Of thickness 300 micrometer, and above it there is diffusion of N-type silicon semiconductor with its thickness very small, 0.1 only micrometer. Very small thickness is this. And there is metallic base at the lower part. There is metallic support or metallic base. And this metallic base becomes one electrode. And at the top you have metallic fingers electrode. Here at the top, this blue lining you can see, this is your metallic finger electrodes. Now, the surface area of this finger electrode is only 50% or even less than the surface area of whole of the silicon semiconductor. Surface area is 15% or even less than the area of silicon N-type semiconductor. So this is the construction of a semiconductor. Now how it works? So you know, initially this is a simple PN junction, all we have discussed just now. Now what happens that initially you have net current 0, no current is flowing, and there is a potential barrier. Now what happens when light falls here? Here there is no biasing, you can see, no battery is connected. Battery is not connected. Okay, so what happens when light falls on it? Initially you have a potential barrier. So when light falls, there is created new electron and hole pair. There is created. Okay. And since it is open circuit, not closed circuit, so initially there was no current, so finally there should be no current. And what happens? So under the influence of this electric field, the positive charges will try to move along this side and negative charge will try to move along this side, and then there is a charge developed on positive side, positive charges, and there is a charge developed on the negative side, negative charges, extra charges. And also you will find that there are not only few charges, many charges are there, and they will cancel or reduce your this minority carriers. These minority carriers will be reduced, and due to which this potential barrier will be reduced. You will have a new potential barrier del V2, and this del V2 will be less than del V1. Potential barrier is reduced, and the amount by which potential barrier is reduced, by the same amount here potential is developed. The amount by which potential barrier is reduced by the same amount potential is increased at the end terminals. And this potential is called photovoltaic EMF or photovoltaic potential. So we see that three processes are very important. Generation. When EM radiation falls, it is generated. Then separation. Electric field separates. It moves positive charges in its direction and electrons opposite to it. So the electron hole pairs are separated. And then collection. Where it is collected? It is collected, here you can see the electrons are collected on these metallic fingers. Here electrons are collected, and lower metallic base the holes are collected, and due to which you can obtain a current in outer circuit. So there is a potential developed at the two ends. There is a potential in the open circuit. Now, in a short circuit condition, when you short this, then there will be a current. So, without applying any external potential, you will have some current in solar cell. So, this is the thing. When light falls, and when you short circuit, then you have a current. And since this current is given by, it is the voltage is developed due to current generated. Current is not given. Current is positive only when current is given, but here current is obtained from it. So why the current is taken negative? And also you can find that these are minority carriers which are shifted along this side, because this is due to minority current, because minority current only flows along this side. This is the direction of minority current, and these are in only reverse bias. So this current is in this graph is in your fourth quadrant. So your open circuit voltage is positive. You can see it has a value greater than 0. Here you can see potential difference is positive. Now here if you connect any load, then current will flow through this load. So this is your open circuit voltage versus short circuit current graph. This is in fourth quadrant. And why short circuit? So when you directly connect without any resistor, when you will connect, then current will be maximum. You know, in short circuiting, current is maximum. But in that case, in that scenario, voltage will become zero. Here you can see. Why voltage become zero? Because in short circuit, when current is maximum, here you can see V is equal to IR. Here R becomes equal to 0. So V also becomes equal to 0. So V becomes 0. So you cannot derive any power. Power is equal to IV. So when V is equal to 0, you cannot derive any power. So in case of short circuit, there the power consumption or power obtained is 0. 0 watt. And when open circuit, when resistance is maximum, this is first case. Now second case, when resistance becomes infinity in open circuit, then I becomes, here I is equal to V by infinity, it becomes 0. So open circuit, current becomes 0. So in these two cases, power will be 0. In any case, power will be 0. So for obtaining power, you should have a moderate value of resistance. You cannot apply a very large resistance because these are very sensitive devices. They cannot sustain very large resistances, and therefore we connect very devices with very small resistances like electronic devices, or we can save this energy in auxiliary batteries. In our spacecrafts, we have solar panel, solar array, which save this energy in chemical form in a battery. So I conclude. For the formation of solar cells, photovoltaic cells, we should choose the semiconductors on certain basis. First criteria is their energy gap. These semiconductors are very suitable for making a solar cell. Now another criteria are optical absorption. So if EM radiations are not absorbed up to PN junction, then all these phenomena cannot take place. Third criteria is electrical conductivity, and not a little less important criteria is availability of all these semiconductors